Hi students, so this is the standard level worksheet for the astrophysics, and I'm going to be doing the first paper, and that paper is actually the May 2009 paper 1, time zone 1, paper 3, time zone 1. So the first question says, this question is about stars. Distinguish between apparent magnitude and absolute magnitude. So here it's important that you understand got your definitions. So apparent magnitude gives us an indication. It's a measure of how bright a star is as seen from the Earth. Now, I'm not going to write these out in full. You do have the actual mark scheme so that you can read them in full there, and you should be able to get it also from your notes and so forth. The absolute magnitude is the apparent magnitude when as seen when the star is 10 parsecs away. So the absolute magnitude, I'll just put AM for absolute magnitude, is the apparent magnitude. What the apparent magnitude of the star would be if the star is 10 parsecs away from the Earth. Alright, the next question here, we give a table and it's given some information. We have the absolute magnitude, so that would be all the stars are 10 parsecs. So this is a very good comparison. You can actually really compare the brightness of the stars because they're all from the same distance away. So we got those. Then we get the apparent magnitude. This is how it actually appears on Earth. And this is your spectral class. This gives an idea of the color and the surface temperature of the star. So which of the three appear brightest on Earth? Well, we'd obviously go to our apparent magnitude because this is star from the Earth, and the scale works a little bit strange in that the smaller the number, the brighter it is. So it will be the +5 of Acamar. This one over here, Acamar. Will be that one because that is the smallest value, +0.5. Now estimate the ratio of the LA to LE. Now LA is the luminosity of Acamar and LE is the luminosity of EG129. Now in doing this, if we want to estimate the luminosities, we would need to use our absolute magnitudes because this gives us an actual indication of how bright the star is and therefore what the actual luminosities are. Now, we've got LA as to LE, and I'll just work on the side here. We've got Acamar is at -3. Now I'm going to do this in full. It may seem a little bit long-winded, but let me do it in full. And this is 13, and we know the scale goes up, so it's I'm going to just do it like -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now the factor increase between each one as you go from there to there, there's a factor increase or decrease actually as we go from here of 2.5. This one, the -2 is going to be 2.5 times less bright than the -3. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 factors. 2.5 to the 16 factor difference. Now LA is actually going to be brighter than the EG129, so this would be 2.5 to the 16. I hope you understand this idea of the 2.5. Remember, they set up the scale for your apparent magnitude, and in the beginning it was from 1 to 6. So 1, 2, 3, 4, 5, and 6. These were the classification, and star 6 was, or star 1 was 100 times brighter than star 6. And if we do this number of factors, there's actually 5 factor difference here. So x to the 5, some factor is equal to 100 times, and that x worked out to be about 2.5. So as you go from a star 6 star to a star 5, you have to times the brightness by about 2.5. It's not exactly 2.5, but it's somewhere around there. Okay, and when we work this out, when we find that out, we get a value of about it works out to be about 2.3 times 10 to the 6. That's the value that it works out to be. Okay, good. So let's go on to the next question here. Now it says, show that the distance of the star from the Earth, from Acamar, from the Earth is approximately 50 parsecs away. So we're going to use this formula over here, that m minus m is equal to the 5 log of d over 10, where d is measured in parsecs. So we've got that situation there. If I rearrange this formula, I'm actually wanting to work out this d. So in doing this, let me just go back up here. We are looking for this. So we see this would be the big M value, and this would be the small m value there for Acamar. So it's plus 0.5 and minus 3. So bringing this down again, sorry, having to go up and down, this is 0.5 minus 3, make sure you get that right, is equal to 5 log of d to the 10. Now I'll just work on the side here. That's going to obviously equal to 3.5 divided by 5 is equal to log d to the 10. Now you've got to be quite good at converting from your log form to exponential form. So 10 to the 3.5 over 5 is equal to d over 10. So it's going to be 10 times that is equal to d. And when we do that, calculation, we get a value of around about 50 parsecs. That's going to be. And then finally, for this question here, state and explain which of the stars in the table is a white dwarf. Now we know a white dwarf is quite a hot. It's got a hot surface, but because it's so small, it hasn't got a high luminosity. So here we get a spectral class. We've got the same spectral class. So the temperatures of the surface is about the same. But here the absolute magnitude of this is minus 3 and this is plus 13. So this must be actually, the luminosity of this must be far smaller than Acamar. And so this over here would be your white dwarf, which is the white dwarf is relatively small, and therefore the luminosity depends on the surface area. And so your EG 1 to 9 would be your white dwarf star. Alright, going on to this question over here, this E2 question. This question is about cosmic microwave background radiation. The graph shows the spectrum of cosmic microwave background radiation. Now, we ask here, the shape of the graph suggests a black body. So we have Wien's law is going to apply. And a spectrum to which Wien's law applies. Use a graph to estimate the black body temperature. So we've got Wien's law, lambda max times the temperature is equal to 2.9 times 10 to the negative 3. I'll leave out the units there. Now you've got to do this. Now on my diagram here, it's not very clear, but it's around about there. Now each of these, this is actually 0.1 double, so we're about 1.0507, and be careful, millimeters, so times 10 to the negative 3 meters. Please make sure that you're really careful to look at that. So your temperature therefore is going to equal to 2.9 times 10 to the negative 3 divided by 1.07 times 10 to the negative 3, and as you can see those negative 3's will cancel, and you get a value of about 2.7 Kelvin. Then explain how your answers evidence in support of the black model of the Big Bang theory. Well, according to the Big Bang theory, the temperature of the universe and the radiation is in the distant past is very high. That's straight from the solution. So what we had with the Big Bang theory, with the Big Bang model, is that you had very high energy. You had very high energy at the start, and it was contained within the and that is spread out through the whole universe. So what's happened is that as the universe has expanded, so the temperature has dropped, and the wavelength of the light, of the wavelength of the radiation has increased. It's stretched as the universe has stretched out. And then state and explain another piece of experimental evidence in support of the Big Bang model. Well, there's two. We have Hubble's law, which shows that because in Hubble's law he basically showed that the universe is expanding. Then what did it expand from? It must have in the distant past been a point, or it must have come from somewhere, so we could reverse the process. It would click, it would go down to a single point. And we also have the Doppler effect, which indicates, which is basically what Hubble saw, that galaxies are moving away, and therefore if they're moving away, they must have been much closer to each other. They must have been much closer to each other in the past. Okay, so that's that for this paper. If you have any further questions in regard to, please come and see me. I'm not trying to give detailed answers always, but remember, when it's 2 marks, you must make sure that you have 2 clear points, so that you can get your points, your marks for that. Okay, thank you very much for that one.